Hello everyone, welcome to my channel. Today I want to explain a statistical model which is called PCA or Principal Component Analysis, which its main purpose is to reduce the number of variables that we have in our dataset, but at the same time trying to use as little information as possible. We're going to do this exercise with R, applying some simulation, and at the same time at the end of the video we want to apply this model with the real data, which is based on global YouTube statistics. This dataset can be found in Kaggle, and also we leave the links below the description. If you like this topic and if you like the video, please subscribe to my channel and click the like button. Let's go. Alright, before to get started with R, I would like to explain first the mathematical framework that is lying behind this model. So imagine we have two random variables like x and y with normal distribution, and we form two random vectors. These two random variables can be height or wave, as you can see here in this data frame. But at the same time, this is the frame that can be considered as a matrix that I will call X. Our main goal here is to find another matrix A such that when we multiply X by A, we obtain a new matrix where each element is actually a linear combination of the original variable. That means that the new variable zeta is a linear combination of height and wave. And that's really important here. But the point is, how do we find A? And once we find it, what is the meaning of A? And how it can help us to reduce the number of variables? To understand that, we need first to understand the mathematical concept of rotation. So let's go for that. Alright, imagine that 95% of the observation are lying inside this ellipse. So you see clearly here the picture, you see two lines, a green line and a purple line. The green line is called the major axis, while the purple line is called the minor axis. So how do you think this ellipse will look like if we decide to look at this from these two new lines? It will look like this, right? Well, that is exactly what A is doing when we multiply X by A, obtaining a new matrix, zeta, because A is rotating the ellipses to the new axes, which are the major axis and the minor axis. All right, but how do we get there? I mean, how do we obtain the matrix A? To get there, we need first to understand very well a new concept, the covariance. All right, so imagine that this is our graphic representation of our data set. So you see at the axis, when the wave increase, also height us in a certain direction. The same happen in the opposite way. This direction is called the direction of the maximum variance. And when we understand later on why we call the direction of the maximum variance. For now, you need to understand that the covariance is a measure of relationship between two variables. So when x increase and y increase, we say that the covariance between x and y are varying in the same direction. That means the covariance is positive. Why? When x decrease and y increase, we can see clearly here the relationship between these two variables are exactly the opposite. So they vary each other in the opposite way. So when that happens, we say that the covariance is negative. And this measure can be collected in a mathematical object that we call matrix, in this case the covariance matrix, where in the main diagonal we have the individual variance of each variable, while off the diagonal we have the covariances between them. But to keep digging into it, we need first to explain a little bit of matrix theory. So let's go for that. An important concept in linear algebra is the symmetric matrix. We say that we have a symmetric matrix when each element of the diagonal is actually a mirror reflection of each other. That means that the covariance between x and y is actually the covariance of y and x. They are the same. Also, from linear algebra, we know that every symmetric matrix can generate an ellipse, a parabola, or an hyperbola. In our case, our covariance matrix is generating an ellipse. This ellipse. How do we know that? Well, in mathematics, every quadratic form can be represented by this expression. Using sum notation, we end up in this equation that also have an equivalent representation with matrix notation. If we put all together, we end up having just a product of matrix and vector. Since we don't want to end up having a line or point, we just equate the linear term to 0. This expression can be even more simplified using submatrix notation, having this expression where the matrix in the middle is called the main matrix, M. The B transpose is actually the vector that is included linear term. Sometimes, depending what notation you're using, you can include also the independent term, C. And the matrix A is not a rotation matrix here, it's actually the covariance matrix. But since I like to respect the notation of my source, I call it just for now A, just for this slide. At the end, we have this matrix where A, as I say, is a covariance matrix, which I will call from now on sigma, capital sigma, while B is a vector that is including the linear term equal to 0 plus the linear term, the independent term that we use later if it's necessary. All right, this is now our M matrix, having the covariance matrix as a submatrix plus the independent term with linear term equal to 0. As you can see here, from linear algebra, we say that this matrix is definitely positive if the main determinant is different from 0 and every single submatrix that we form inside this matrix is as well different from 0. This property allows us to say that this symmetric matrix is generating an ellipse. All right, let's calculate now the covariance matrix. Our covariance matrix is actually X transpose times X. But since we apply transformation over X, our new covariance matrix will be now zeta transpose zeta, having this final expression here. And we will call this expression bar covariance. The relationship between these two covariance matrices pass through the determinant and the trace, since both expressions have the same determinant and the same trace. We define the trace as the sum of the main diagonal of the matrix. In this case, the sum corresponds to the sum of the individual variance, the variance of X and the variance of Y. And we call this expression the global variance. While the determinant will be called the area of dispersion. Basically, when the determinant is decreasing, the area of dispersion is narrow. While when the determinant increases, we can see a wider area where the points are. All right, let's get some visual intuition into it. So as you remember, we have this graphical representation from our data frame. So when wave increases, also height does in a certain direction, the same the opposite way. We call this direction the direction of the maximum variance. When we multiply x by a, we rotate these ellipses having this expression. So now with these two new variables, zeta1 and zeta2, we see that when zeta1 is increasing, zeta2 also that, but pretty much less. And now the direction of the maximum variance is horizontal, while the direction of the second maximum variance is vertical. We know that both of the traces are equal. That means the covariance matrix and also the transform covariance matrix are containing exactly the same information. So they have the same global variance. So if that happens, that means that despite having the same global variance, the distribution of the variance between the variable has changed. Now, after the transformation, zeta1 is having roughly 95% of the variance. That means that zeta1 is having the 95% of the information. So if we are allowed to keep just one of the variable, right? If we decide to lose just 5% of the information, having just one variable is enough to explain the 95% of all the information. And that is exactly what principal component analysis is doing. We reduce the number of variables just by losing a little information, in this case 5%. Sometimes can be even 3 or 2%. So now with that, we have explained the mathematical framework. We are ready now to go into R. Let's go, Free. All right, we're finally are in our studio right now, so let's keep learning how to calculate the PCA. So first, load in my library. In this case, teddy bear, matrix, psych, and patchwork. Psych basically for principal commonality, library for plotting, matrix stuff to use some functionalities in for matrix, and the very well known tidyverse. All right, let's start defining a variable or random variable, which is x. You remember it was x with 0 mean 0 2, just look at it like that. And also y, returns on some observation, mean 3, and standard deviation 2. If I just leave it like that, let's go ITF, what do you think is going to happen? What do you think? What's going to happen is exactly that. There is not a relationship between them, so I want to force a relationship. Let's say height is x plus 0.4 y. Y waved is y times 0.7 times x. This is how we simulate the relationship waved. So now we don't have nothing yet. What's going on? Hey, wait, x and y, height, height, and weight. Now we have a relationship. So let's calculate the covariance matrix. These are covariance matrix, or variance of the height is 165 and the width is 4.51. While the covariance between them is positive and it's 2.32. It's a symmetric matrix, as you can see there. And something that I never say in the slide, I left the question open. I just wanted to answer the question here. Is how to calculate the matrix A. Well, the matrix A is actually the eigenvectors, the collection of eigenvector of the covariance matrix. Right? A and S. This object contain the eigenvalues and the eigenvector. We have here that the first column is the first or the second column, since they are orthogonal between them, are pointing in the direction of the first maximum variance and the second maximum variance. The eigenvalues is telling us the variance. If I sum all together these two values, I will obtain the global variance. So before to calculate, I will calculate now is zeta matrix. If you remember, the zeta matrix was x times A, right? We already have A. No, we don't have it right, actually. So let's calculate it real quick. The eigenvector, and this is our matrix A. So the new variable is going to be xdf times zeta, right? But xdf is a data frame, it's not a matrix. So we need first to get a matrix, and it will look like that, right? And I will call this matrix capital X df. So if I want to get zeta, I just multiply x df times A, and this is now the zeta matrix, the new variable, but I want a data frame. All right, This is now the data frame, and I will change the variable. Z1 will be V1, Z2 will be V2. There you go, and I will call this matrix ZDF. Now we have the new data frame. So if everything is correct, if I plot these two new variables, how do you think it will look like? If you follow the slides. Exactly, it will look horizontal. So let's put these two plot together, right? I will call this plot the zeta, and this plot I will call it px. Alright. The zeta px. Alright, this is how it looks like. So let's put it first, let's put it a bit nicely. Alright, and that one will be start ellipse, color black, size 2, and the color will be blue, alpha 0.2. It's gonna be B zeta and Bx. It's gonna be start ellipse is gonna be color black, size 2, and what else? The color be red, alpha 0.2. And now let's check the difference. Start ellipse require the following missing aesthetic. Yeah, because we haven't say what variable we're gonna plot. It's gonna be zeta1, zeta2 for p zeta, and also height and waved. Yeah, finally. So this is the original variable, wave and height, and that is the new variable. Let's check it out now. How the variance, the proportional variance, change between them. So if everything is correct, the trace is of S, the trace of S okay, the trace of S should be exactly the same as the trace of zeta, but we haven't calculated yet. So we're gonna first calculate zeta df. So 6.16 and 6.16, and also the determinant of S should be the same determinant, 2.35 and 2.35. Okay, so let's make a list. Global variance X, and also global variance zeta, area of dispersion X, and also area of dispersion zeta. Unexpected symbol is global variance trace zeta. That's not a point. It's a comma, and we create a table. So the global variance of both data frame are the same, and also the average dispersion. That means we still have the same information. And I will call this data frame info table. Okay, now let's go for the proportion. So if I get df and I want to calculate the variance, both variable, I get that, and as a table I get that. At the same time, let's do the same for xdf. Alright, and let's put it together in also a data frame. Okay, and I will call var prop table. And now let's check it out how the proportion between them has changed. Don't get lost. We already proved here where we show that the global variance between them are the same, right? So var prop, what the only thing we need to do right here is just divide by the trait of s or the trait of s of s zeta. So if we do in both way, we should obtain the same data frame. So before the proportion was 73% and 26%, and now the proportion has changed to 94% to almost 6%. Let's check now what's happened if we use now the trace of zeta value. Should get exactly the same. 94.3 is alright. So applying the transformation, zeta 1 is having now the 94% of the information, while zeta 2 is having just around 6%. So if we decide to lose just a little bit of information, around 6%, we just keep one variable. That's not really important when you have to, but when you have 10 or 15 variables, that's become really important. Alright, that's it for now. That's the simulation and that's the explanation. Let's go now to analyze real data and to seek the potential of this analysis. Let's go.